To end this lecture, we're actually going to summarize all of the data structures we've implemented up to this point. So all of them basically do the same thing, which is solve something I call the search problem. Basically, given a stream of data, I want to get the information I want from that stream. So for example, a website user posts something to a personal page, and we want to serve that content, whatever it may be, only to their friends. This is a very old social network from back in the day, and you want to make sure that only the people you want to be able to see things can see the things you want them to see. Another one, given logs for thousands of weather stations out there, display a nice weather map for the specified date and time, right? I want to show this nice heat map showing the current temperature in some place. So all of these things are the search problem, and the data structures we've been building so far have been to solve the search problem for various domains of interest. So for example, we had the list, the map, the set, the priority queue, and the disjoint sets operation, and all of these in some sense can be interpreted as part of the search problem. So in this case, the list operation, or say the list data structure, abstract data type, it has the add and insert storage operations. These are the key things, the way you put stuff in. Maps, you put a key value pair. Sets, you add. Priority queues, you add. In disjoint sets, you connect things up. Okay? How do you retrieve information back from them? Well, with lists, you get something from an index. For maps, you get a key. With sets, you ask if it's contained. With priority queue, you ask for the smallest thing. And with disjoint sets, you say, are two things connected? And the information you use to actually retrieve things is different in each. So we have the index, the identity of a key, the order of the key is what we do with priority queues, and with disjoint sets, we're doing two int values. Okay? So all of these different data structures, all these different abstract data types, they solve some problem. If you need to do this, right, I need to get back items by their key identity, the map is your tool of interest. So let's think about how we can actually implement each of these. We've seen a bunch of these, so I have my answers here, but I'm going to make up a new slide here. So what are all the ways that we were able to implement sets and maps? I'll start listing some. So one way is to do a binary search tree. I'll just put BST. And a binary search tree will work, but I'm going to say that its performance is not particularly good, right? I'm going to do it mark it in red. If we have a balanced binary search tree, maybe we have a, I don't know, we'll do 2-3 tree. Okay, so I'm just doing this totally off the dome. It probably won't match the slide below. 2-3 trees, by contrast, they actually have great performance. So I'll mark it in green. We could also do LLRBs. We could do, let's say, hash tables. And yeah, those are all some different ways we could do it. So these all here, all lumped together, right? Because they're all part of the same family, the same core idea. So I'll do this little rounded square. Here we go. I'll send it to the back. I'll make it light. It's a little dark. Let's maybe make it a little nicer. So each of these, that's too light. Okay. No, I don't know. Maybe we're just going to end up where we were. Okay. Yeah, doesn't matter. Okay, good enough. And so in this case, each of these could be used to represent a set. Now it turns out, actually, I'm going to draw a little line here to represent this fact, that a set and a map are deeply intertwined data structures. In fact, both of them use key identity, and the only real meaningful difference between the two is that a map, instead of giving you a true-false value, it gives you something else, right? So if you give it horse, maybe it gives you a picture of a horse, whereas a set would just say, yes, horse is included. Okay. So I'll add all of these lines to say these are different ways of doing things. Okay. Oops. So sets, maps, these are different ways of doing it, and there are more than this, right? I mean, there's skip lists and splay trees and AVL trees and all kinds of other things you could try and imagine. And hash tables, by the way, there are different ways of doing it. In fact, actually, I'll enumerate them separately. So we have separate chaining hash table. And then there's also the one we didn't mention in lecture, except in the extra slides, which would be linear probing. Oh my gosh, I can't believe I did that. I used to always get tripped up on this word, by the way. I don't know, that's a little embarrassing, but whatever. You don't always have to spell correctly. Not in the modern era of computers with little red lines. It took me forever, by the way, to get this one right. Definitely. My God, I always did that for ages. Like, I eventually purged myself of writing definitely. I don't know what it is, but anyway. All right. How about stacks, right? So the stack is an abstract data structure, or abstract data type, that we've used in the past. And there's a bunch of different ways we could implement that. We could do, for example, a linked list. We could do, I don't have you here, and I'm not going to go looking for you again this time, to ask you what you might do. But we have linked list, and we have, let's say, array list. We'll call it a resizing array. And these are two different ideas here. Okay. And in some ways, these are like a linked list, and these are like a resizing array. Okay, so there's some parallels here. I'll draw in a little box here. Okay. Gotta fix the color. We gotta send it to the back. All right. So how about linked list, resizing array? These were part of stack. I don't think they don't deserve a box around them. And so you might try and do the same exercise for the rest without me telling you. No. Okay, well, a list turns out to be pretty similar to a stack. So I will do this. Okay. Today we just did the priority queue. So the priority queue, we think, what are the different ways of doing this? Okay, well, in this lecture we talked about how we could do an ordered array. And we said that wasn't very good. We talked about using a BST, which, I mean, it's kind of good. It's arguable. Actually, we should say balanced. We'll do LLRB. It's left-leaning red black tree. So this kind of works. I mean, it has good performance. I'm going to call it yellow during this one. So tricky because it takes some modification, but it actually ultimately has good performance. A hash table of some kind. Not very good. It'll just be slow. And what we did in this lecture was we introduced another implementation of this abstract data type, which was a heap. Okay. So I won't do all the disjoint set ones because probably you're getting a little fatigued from watching me draw diagrams. So I'll just switch to the one I did last time. We'll compare and see how I did. Okay. So in this case, I used blue and red. Okay. And this is basically, well, as you note down here, this is from a previous semester's lectures. Where this is what the students came up with. I asked in class, we threw them all in there, and this is the creation I had there. Okay, so a pretty similar idea, although in that case I called this blue instead of yellow. And so there's different taxonomies you might have. But I just wanted to draw this picture, right? I mean, the exact picture, I don't want you to memorize this picture. I don't want you to copy it down on your cheat sheet. Well, I guess you can, but it really should be something you construct, right? So there's different ways you might taxonomize these. These are two different taxonomies. This is from students in the past. This is the one I just did. And I think it's important and interesting to keep these things in mind. Okay. So that brings us then to an interesting notion I want to bring up, which is the distinction between an abstract data type and an implementation. So sometimes abstraction actually happens in layers. So a priority queue, as you noticed, I said one of the ways we could do this is a heap, right? But what is a heap? Well, a heap is a heap ordered tree. And what's a tree? Well, there's actually 5 different ways of doing that. We had approach 1A, 1B, 1C, 2, 3. Actually, no, I left off an important one, which is the one actually we did in lecture. So we'll put that in. So this is approach 3B. And so all those will work. This one has the same size line. Good. So all those will work. And they have the different trade-offs, but they should all be pretty fast. How about an external chaining or separate chaining hash table? Well, it's an array of buckets, but what's a bucket? Well, it could be an array list, it could be a resizing array, it could be a linked list, it could actually be a binary search tree. You could build a hash table where each bucket is a binary search tree, though all of these are also fast, because one of the rules with buckets is we always resize, so everything is constant size. That is, each of these should all be below some constant, right? So it doesn't matter whether it's a list or a tree, it's still going to be a constant size, so they'll all be fast. Okay. And so that's actually a really important point. And in theory, you could build something like this. Say for project 2, you could imagine you're building a database. You could have a database which is a table which has a da-da-da, and it could just be this gigantic hierarchy of ideas. And this is, I think, an important notion. And again, one of the main goals of computer science, right, trying to learn it, is learning how to manage complexity. And I think this is these diagrams give you a sense of how we can taxonomize our tools for managing complexity. And what's important to note that often the things happen in layers. Now, there are also some specialized searching data structures. So occasionally, we won't just have a list, but we'll also have, say, a stack or a queue or a double-ended queue. And each of these are basically, a stack is just a list where you can only take things off the top. And a queue is something where you enter at the top and you enter at the bottom or whatever else. And a double-ended queue, you could do either end, but you can't do the middle. And so those are all specialized versions of lists. And it's just nice to note that sometimes that's the case. Same deal with sets and maps. You can have sorted sets or sorted maps. In Java, they're actually interfaces, or maybe they're abstract classes, I don't actually remember, called sorted set and sorted map. And I'll mention that with priority queue, you could have a minimum oriented and a maximum oriented priority queue, but typically we don't actually consider those distinctions since we can always just provide the opposite comparator. So if we want to find the most harmonious thing someone wrote, we could just give a comparator which does the opposite of the unharmoniousness comparator. Okay, so this summarizes. This isn't the very last data structure we're going to do, but I do want to, at this point, now that we've covered all of the really core data structures, it's good to reflect here and say that a data structure, this course, simply put, is just a particular way of organizing data. And then so far, what we've done is we've considered a lot of the most fundamental abstract data types, right? We've talked about maps and sets and priority queues. We've talked about, disjoint sets, which is not quite as fundamental, and stacks, which are really just a kind of list. But these four right here, especially these three, set, map, and list, those are the head honchos, or the most important of our abstract data types out there. And we've also seen the common implementations, right? We've seen all of these, and we've seen their trade-offs. We've drawn these diagrams. We've decided these are red, this is yellow, this is green. And a lot of what you'll see moving forwards as someone trying to manage complexity and write programs that are fast is knowing, first of all, what the abstract data types are that will make your life easy, and second of all, which implementations are actually going to make your implementation faster. Now, in practice, often any of the good implementations is good enough, though occasionally maybe you'll find you want a tree map versus a hash map. But to be quite honest, that doesn't happen super often. That's not usually a big piece of your choice, but often when you go to data structures or you're really trying to push performance, when you go to data structures, I meant to say when you go to interviews or whenever you're really trying to squeeze the last mile of performance out, that's where the implementation differences come up. And so we'll do two more data structures in this class. There'll be the quad tree, and then there'll be the graph, and that will be all we got for this class. Now, if you want, you can go to Wikipedia, by the way, and you can see that we've done a lot of these things. So we haven't done all of the abstract data types. I mean, you'll notice that there's something here known as a multi-map. There also seems to be a, actually, that's pretty much the only one on this list we haven't done, right? So we got multi-map and multi-set, but we've done all the rest. An associative array, I'm not sure how that's different than a map, but I guess we'll look on Wikipedia in a bit. But these are our abstract data types. These are different ways of structuring arrays or array-based data structures. We have our trees and so forth. And so we've covered a lot of what's in this diagram, and we'll do a little bit more in the future. Okay, that's it for this lecture, and I'll see you next time.